Okay, everything should be working. Hello, everyone. It's me again. Blah. I can't speak today. So, what's this is going to be is that we're going to go over the first practice paper for mathematics. Now, the exam is coming up in 2 days. It is currently about 10 p.m. on Wednesday when I'm doing this. So I just want to make sure everyone understands the answers so people can learn from them. Okay. Now let's get to this. All right. Now, number one should be fairly obvious. I probably don't have to explain this too much. You've got A and B here, two vectors, and you've got a simple algebraic expression here. So 3A is going to be equal to B. So if we times A, which is regarded as 2 minus 3P, and we do 3A, that's going to change this 2 to a 6, and this minus 3 to a 9. Fairly simple stuff. And we know that this is now equal to B, which is 2Q R. So you're left with 2Q equals 6 and minus 9P equals R. Now, first things first, we can essentially say that, okay, Q is 3. That's a very easy thing to say. So we know that either A, B, C, or D will work. Okay? Now, for P and R, okay, there are a lot of case studies that could work. Okay, it could be P equals 0 and R equals 0. That's perfectly fine. It could be that P equals 1 and R equals minus 9. There's tons of options. But the main thing here to recognize is that R is equal to minus 9P and P is equal to P. Okay? So functionally saying, we're essentially just saying that R is minus 9 times P. That's the main thing. Now, we could also represent this P as just some other number. So let's say P is equal to A, therefore R is going to be equal to negative 9A. Okay? Which then shows you that A would be correct here. Okay? The other cases are correct as well. So 0, 0, minus 1, 9. Yeah, so P and R taking any values. It's not quite like any values, because any values would include on top of that something like a something like another kind of number. So it would not exactly be that. We specifically say real number because we kind of want to include real number within this. It's not just value, it's all numbers, essentially. Just a bit more general. Okay, number 2. So, if ST and U are linearly dependent vectors, which one of the following statements is correct? So we've got S can be expressed as a linear combination of T, U, and V, and there exist non-zero constants alpha, beta, gamma, and... It's not delta. Is that a sigma? That's sigma. Alpha, beta, gamma, and sigma, such that alpha S, beta T, gamma U, sigma V equals 0. Now, most people will probably go for A and B here, but most people were surprised to see that it's E. Okay, why is it E? Okay, so it says here, one of the ST and U vectors could be the vector. Okay, actually, let me explain why it's not A and B. Okay, so this can be the case. S can be expressed as a linear combination of T, U, and V. However, this isn't necessarily correct in a linearly dependent vector. It could be that S is a 0 vector. It could be technically all 0 vectors or something like that. It doesn't necessarily mean that they could be expressed as a combination of the others, okay? The second one is what most people go for. And this isn't exactly perfect, mostly because most people think this is the definition, but this isn't specifically correct because it's not really like, how do I put this? It's not, so you guys know that for linearly dependent vectors, you want values of alpha, beta, gamma, and sigma here to essentially not be 0, okay? And then you're going to get something that equals 0, okay? So you want non-zero constants that give you that, okay? This, however, does not rule out that one of these vectors could be the 0 vector, okay? Because that would also bring in this detail and complexity that isn't covered by this. So we'd be covering the next three. Now, it's not C or D, because C says none could be the zero vector, which is false, because they could always be the zero vector. And D says one must be. We don't say must be. Okay, must be is quite a strong thing. So we go for E. One could be the zero vector. So that's going to be correct here. Because A and B are what people usually think, but they're not sufficient to actually cover this. Plus they're not technically correct. Anyway, for number 3, hopefully this should be fairly obvious, but I'll just cover this. Looking over these, we've got to remember that matrix multiplication is not... There's a word for it. Okay, so in most multiplication, it doesn't matter what order you do it. 3 times 5 and 5 times 3 is exactly the same thing. However, if I times 2 matrices together, such that AB, and we've got BA, they are not going to be equal together. I think it's commutative. It's commutative multiplication. So these aren't the same. Okay? So we're looking out for something that breaks this rule. Okay? Let's, for example, look at ABC and ABC. Okay? Now, this looks like it doesn't work, but it actually does. If you sort of think about BC being multiplied together. Because this technically is in the same order, it doesn't break any rules, if that sort of makes sense. It's ordering, okay, because it's still ABC, ABC, so it doesn't really matter. This one here, again, doesn't matter either, because it's factors, okay? So you're not actually affecting anything. Now C is the one that's wrong. As you can see here, if we expand this right side, we get the A matrix squared, and then you've got plus AB matrix, then the minus AB matrix, and then you've got you've got minus B squared, pardon me. You've got a minus B squared matrix. Now, in order to get that C, we'd assume that these cancel out, but not so. Because this isn't actually AB, it's BA, I believe. Yeah, this is negative BA. These two would not be the same. Therefore, they're not going to cancel out. Therefore, you're not going to get that result. So C is correct. The same thing occurs in D as in B. And then in A, it's actually showing you the correct form of it. Okay, so E, no, not A, can't. You forget the letters when you do maths. In E, you can see that pretty much it's the correct form of C. C is cancelling it out improperly. Okay, now in 4, you can see that the answer is that there are no solutions. Now, why is this? Well, it's actually quite simple. If we think about... Let's just think about this matrix up here as like an equation system. So you have minus x1 plus 2x2 plus 0x3 equals 2. And then you've got something like 0x1 plus 3x2 plus x3, or 1x3, is equal to 4. So far, so good. Okay, this is how it would usually go. But then we look at the final one. 0x1 plus 0x2 plus 0x3 is equal to a half. Well, this is wrong, okay? The fact is, if you're timesing everything by 0, you should not be getting any solution, essentially, because everything is 0. So if you were to even put in x equals 0 here, it wouldn't matter. You would never equal a half. So what we say here is that there's no solution because nothing satisfies this at any capacity, okay? Essentially, this is a type 3 echelon matrix here. If you have a type 3 echelon matrix and the entire row of zeros adds up to a number that isn't 0, then essentially you have no solution, okay? Because it doesn't work like that. Hopefully that's fairly obvious. Okay, now, this is the one that most people have trouble on, okay? These are systems of equations, okay? So there is a distinct thing with systems of equations, okay? So, yeah, hold on, let me think about this. Yeah, so there is, I think of this, yeah, okay. So there's essentially 3 different ways it can go. We qualify this by variables and equations. So if your variable number, essentially the number of variables you have, or unknowns, is larger than the number of equations, which is going to be our first one. If the variable number is smaller than your number of equations, and if it's equal, okay? So variable equal to equations. What this essentially determines is what solutions you actually get, okay? So you can see for 5, for our top one here, that you get no solutions or infinite number. Now, why actually is this? So let's write it down, okay? So imagine, if you would, I have like 7 unknowns here, so they all have their unique numbers. I'm just writing in a circle here. I've just got 7 of these. 1, 2, 3, 4, 5, 6, 7. Okay, so there are 7 unknowns, and then, oh, hold on, 6 equations. Yep. So the thing is here, you want to match the number of unknowns you have to equations, because essentially an equation is giving you information. It's giving you information about, if I add up these, how many do I get? And if you have the same number of additions as you do variables, you can cancel them out neatly. It sort of makes it a lot easier. However, if you have more if you have less equations than you need, then you're essentially missing out information, okay? Now, let me go through specific things here. You can have a no solution here. Imagine, if you would, that I had something like S, T, U, V, W, X, Y, Z. This is like 8 variables, right? Hold on, let me just remove that last one then. So this is 7 variables, right? And I can have a 0 solution, because I can essentially say that these could all be times by 0, like we've seen in the previous question. These could all be times by 0, and I could have like nothing. Essentially, I could have something that like equals 5. This would be false, so this is possible. Okay, remember, as long as you have these equations, there's always going to be the possibility of a 0 solution. Okay, you could have no solution to this. However, an infinite solution is a little less easy to see, so I'm going to try to sort of show this. Okay, an infinite number of solutions is essentially gained from having a variable left over that still doesn't get a value. Okay, so for example, if you're left over with like x is some variable of y, so x is 2y, and z is 3 plus y, and then y is equal to y, and this is what you're left over with, then essentially you have infinite solutions depending on the value of y. Okay, this just works with the cancellation steps. Okay, doing one of these in cancellation is a bit tricky, but essentially that's the logic you need. So let's mark that. For the top one, okay, when the variables are in larger amounts than the equations, you have either no solutions or infinite solutions. Okay, now what about when it's smaller? So let's look at number 6. All right, so for number 6, it says the solution is E. Either there is a unique solution, or there is no solution, or there is an infinite number of solutions. Now, what we've added here is the unique solution. Why? Well, what we've now got actually is more information than we actually need. We've got 7 equations for 6 unknowns. Okay? To be honest, you can essentially, just the more equations you add to the number of variables, the more information you get. It's useless, but you can still use it in a way, if that sort of makes sense. So for this one, you have the same state as we did last time. So let's write down 6 unknowns. So this is just going to be 6 lines to represent the 6 unknowns. Oh, dipped. Oh, nothing's going on. There we go. It's very weird. So that's 5 and that's 6. Okay. We don't know what this value is, right? So we don't know what. Let's just go for T. No, let's go for U, V, W, X, Y, and Z. So these are our variables, for example. If we have 7 separate equations going into this, all right. Now there's always the possibility of a 0 solution. Okay, setting the entire equation to 0 and just getting 0 out. That's always possible. Okay, always possible. Now to get an infinite number of solutions, again, you can find a way to sort of figure out that you've got two equations that are sort of similar to each other. So imagine, if you would, that we had an equation that was 3u plus 3v plus 3w plus 2x plus 2y. Oh dear, that's completely gone wrong. Mixed up the numbers halfway through. It's very unusual of me. Okay, and that's one of our equations, and this would equal something like 6. Okay? And then we have an equation that looks like this, just with the 2's replaced. What's important to recognize here is that these two equations are essentially factors of each other. Okay? And this is quite possible. When you have more equations than you need, you may get equations that are essentially factors of each other. Of course, the more variables you have, the less likely that is, but it is still possible. And that's what we're concerned about here. Given that these two equations are essentially the same equation, they're going to represent an infinite family of solutions because they're essentially representing the same information. So if I end up at the end of this with this equation and it's not cancelled out, then you essentially get this infinite family of solutions that could work. So that's one thing. Now, for the unique solution, okay, there is a way of doing this. Now, most people know that when variables is equal to equations, you can get a solution out of it. Okay, so what you can do is if you have a lot of equations and then you have an equation like, I'm just doing an example here. This is just be a short one to demonstrate. Something like 5x plus 4y and then 3x minus 2y equals 3 or something like that. Like if you have something like this. Okay, what you can essentially do is you compress them into each other. If there are 7 equations, hold on, so there are 6 unknowns and you've got 7 equations, it would be better to have 6 equations, right? So what we do is we essentially compress 2 into 1. You add these together. So you have 8x plus 2y equals 18. This is still true, but what it means is that we now have 6 equations for 6 unknowns. Okay? So this essentially gives us the possibility of using a unique solution. We couldn't do this with the last one because we didn't have enough equations. Because we can't take another equation out. We have to, here we're basically recombining them back together. So for that, 6e. Hopefully that's clear. So let's continue. For 7, the rank of the matrix. The rank of a matrix is determined by the number of linearly dependent vectors within it. Okay, so for example, if I had a vector that looked something like this, where I had like 2, 5, and then something like 4, 10, and then like 3, 7 or whatever. If these two are factors of each other, now that means that they're 2 linearly dependent vectors. Okay, this one isn't in this case. Okay, we could also technically reduce the echelon form and count the number of pivots, but it's not as fun. So this is how we get it. And thankfully, the rank here is 2. Okay, because it's got 2 linearly dependent vectors. Okay. And in our example, we can see a very similar thing. We've got 1, 3, 2, 6, and 3, 8. And you can see quite clearly that these 2 vectors are, linearly dependent, or at least factors of each other. Maybe I'm using the wrong word. Factors of each other would be a better word. So the rank is 2. Fairly simple. So it's going to be C there. Okay. Now for the next one. The matrix here is an inverse for all of which are the following values of K. To find the determinant of a 3x3 matrix is fairly simple. You guys should probably know this. It's going to be that top number, this top row, and you're going to times it by the determinant of the lower quadrant, basically the quadrant that hasn't been allocated by the... I shouldn't really have to explain this. It's essentially the row and the... Okay, so for K here, we're going to find the determinant, we're going to do K, and then we've got K plus 1, K plus 3 times together, and then because it's being times by 0 in the diagonal, the other one we're not going to add that. So this is our first bit. We minus the next derivative, which is minus 1 times 0 plus 0, which is just going to be, well, 0, so nothing. And then we've got 2 times 0 plus 0, so 0 again. So this is essentially the determinant, which we know to be K squared plus 4K plus 3. Actually, I prefer to keep it as this, now that I think about it. So, we know that a matrix is can't speak. A matrix is invertible for all values that have a determinant that isn't 0. So we know that this can't equal 0. Now this is essentially like a quadratic, but it's just the other way around. So in this case, k cannot equal 0, because if it equaled 0, it would times by 0, and it would equal nothing. Similarly, k cannot equal -1 from this bracket here, and k cannot equal -3 from this bracket here. Fairly simple stuff. I don't expect most people to get this wrong. So it's E here. All right. Now this one is a bit trickier. To determine which of these matrices to work, you essentially have to say that, okay, so let's establish a rule here. If you have a quadratic form that looks roughly like this, so you have a x squared of 1 plus b x1 x2 plus c x2 squared, then what you're going to essentially want is a matrix that looks like this. You've got a and c in the diagonals, and then you've got something like s and t, where s and t are essentially two values that add up to b. If you want it to be equal between b, then you can literally just write something like this. But that may not always be the case. And in this case, it's explicitly asking for a different thing. So we're going to do something like this. Now, for our equation, we've got x1 squared plus 6x1 x2 plus 2x2 squared. So we know from logic here that a has to be 1 and c has to be 2. Okay? But we can also see that that is the case for literally every single one of these matrices. So we now need to figure out something else. We also need to know that the other diagonal has to add up to 6, okay? So this diagonal can be anything that adds up to 6. Okay, so let's check through. 5 plus 1 adds up to 6, very good. 3 plus 2, that does not add up to 6, does it? No, it does not. So this one is not correct because it would give you something like 5 instead of 6. So that's not correct there. Okay. There we go. All right. So, next one's a bit trickier. Let's with the quadratic form that before exist, okay? And we have a matrix that will be coming from this. Which of the following statements is true? Now, now. You essentially want to say, when does this quadratic form, well, essentially, the major thing is this. Where is the determinant? If it's kind of moving between positive and negative, then essentially you cannot tell where it's going to be. In this case, you've got two definitely positive things. You've got x squared of 1 plus x squared of 2. So these are definitely positive. However, we've got also the plus 6x1, x2. So hypothetically, you could have something below that. And as a matter of fact, if you find the determinant of this, which is 6 squared minus 4, 1, 2, you can see that that is 28. I think it's 28, which is above, which would state that it would have roots and would go into negative territory. So what we essentially say here is that it's not any of the above, because it's not always positive or non-negative, okay? A reminder, positive definite means that the determinant must be always positive. Positive semi-definite means the determinant is always non-negative. Now there's a distinction here. Okay, so positive means that if I have x, it must be above 0. And then non-negative simply means x must be above or equal to 0. That's essentially the distinction. It means it can hit 0, but it cannot be negative. Okay, so here is none of the above. Now, this one's a little easier. If z is equal to x e to the power of xy, which of the following is the value of the partial derivative of x partial derivative of z with respect to x when x equals 1 and y equals 2? So first of all, let's do the partial derivative here. This should be fairly fine. Here we just use product rule to find the partial derivative. So dz dx. I'm going to start by deriving the x, which will give me 1 times e to the xy. And then we're going to add the x times the e to the xy, which should be y e to the xy. because y is being, we're treating like a constant here. So timesing that out, you'd get y equals xy. Now, that's the derivative. Now, what happens if we sub in our values? So if x equals 1, we have 1 times 2 up here. So this is going to be e squared. Then you've got x equals 1, so 1 times 2e2. Yeah. So you're essentially, I don't think I need to teach any of you guys how to put numbers into an equation. But you'll essentially get something like this, which will give you 3e squared. If anyone's confused, this is product rule, by the way. Okay, that's fairly easy, I think. I don't think I need to explain myself much on that. Okay, now we want to figure out what is the value of the second derivative. Okay, so what happens if we do a second derivative of this function here, which is equal to e to the power of xy. So a second derivative, hold on, it's a partial derivative, do excuse me. So if we're partially deriving by x, that means we're going to essentially do the same thing we did before. Treat y as a constant. So we get y e to the xy for our first one, because moving that out, we get a constant times by y. And then if we do this again for the second derivative, we will get times by y again, because remember, e is going to cyclically sort of derive, yes. So you get y squared is equal to exy. Now, when x is equal to 0 and y is equal to 3, so what we do here is we sub that in. So we get 3 squared, e is equal to 0 times 3. Now, shockingly enough, this will give you 9 e to the power of 0. What is e to the power of 0? It's 1. So the final answer is going to be 9 in this case, which is here b, I believe. Let me just double check. Yep, all good. Okay, so it's b. Now, this one, if z is equal to x squared y plus xy squared, where x is equal to t squared and y is equal to t, the value of dz dt at t equals 1 is which of the following? Now, to be honest, I don't think this is too hard. You can sub in values of t for x and y. So what I do is I do z is equal to x squared, which is t squared squared, times the t from the y. And then you've got the t squared in that bracket, and then the t squared over there. This gives you t to the power of 5 over here, and t to the power of 4. Which is equal to z. Now, what's the derivative relative to t? So we do dz dt, and this is simple derivatives. I expect you guys to get this. 5t to the power of 4 plus 4t to the power of 3. Now, if t is equal to 1, fairly simple, right? 5 1 to the power of 4 plus 4 1 to the power of 3 just simply equals 9. And there you go. It's also 13c there, it tells you. What do you know? Anyway. Right, this is a slightly trickier one, so it's not entirely clear, but the answer is none of the above, because all of these are false, essentially. Now I'll show you why they're all false. Now, return to the scale is essentially denoted by the degree of homogeneity of a function. Okay, so if I had a function like x squared times y squared, something like this, okay, if you guys remember, the degree of homogeneity is determined by this. So if I essentially have a function of lambda x and lambda y, the degree of homogeneity is the power of the lambda that comes out of the equation. So what happens if I do lambda x and lambda y here? So in this case, I would get lambda x squared, lambda y squared, which would give you lambda squared x squared, lambda squared y squared, which gives you lambda to the power of 4 x squared y squared, meaning the degree of homogeneity here is 4. That would mean that your return to scale is 4 times every single time. So every time you do this, you're essentially getting 4 times the result. Now the Cobb-Douglas production function has something similar, so we're going to go through this now. Okay, so you have, let's try f lambda k lambda l. This is essentially going to give you a, and then we're going to do lambda k of alpha, and then lambda l of beta. what this gives you is the lambda is going to be to the power of alpha here. So we get lambda to the power of alpha, k to the power of alpha. And a similar thing is going to happen to this one. So you've got lambda to the power of beta, L to the power of beta. Now, as you know, two powers timesing together essentially add. So we end up with, on the outside here, lambda alpha plus beta of our original function, a, k alpha, L beta. Meaning, this is our degree of homogeneity. Now, how can we tell what the returns to scale are? Now, if a return to scale is constant, that means this is 1. Essentially, it's outputting the same amount it did previously. If it's decreasing, it's going to be below 1, and if it's increasing, it's going to be above 1. Okay? Because we do not know if these values of alpha and beta are going to be above that or below that, all we know is if it's above 0, but that doesn't tell us enough. We can't tell if the returns to scale are constant, decreasing, or increasing. Okay? We just can't. Okay, this is because we just can't know the values of alpha and beta. Okay, returns to each factor are diminishing. That's quite false as well. So let's try deriving this partially for something like k. Okay, so if I was to derive something like k, all right. Actually, I don't think I even need to do this. It's actually the return to scale for k is actually represented so simply by the lambda alpha. Okay. It's alpha, again, but we don't know alpha, so we cannot accurately determine if the returns to each scale factor are diminishing. Actually, as a matter of fact, if alpha was something like 5, it would be specifically increasing, wouldn't it? So that can't work either. So it's E. So none of those are correct. Now for number 15, we're going to use implicit differentiation. I'll just go over implicit differentiation one more time, just in case anyone quite didn't get it. Implicit differentiation is eventually where we're going to derive the entire function, by a certain variable, and then when deriving variables that are not the variable we're specifically deriving, so for example if we're deriving by x and we come across a y, we essentially put the derivative onto that just to amend it. So here I'm deriving by x, so we're going to x squared goes to 2x. Now here I've got 3y squared, so if I derive it to 6y, I need to times it by dy dx to make it valid. 1, simply put, derives to 0. Okay, so now I rearrange for dy dx. So dy dx is timesing by 6y, but that's going to be equal to negative 2x. And then we divide by 6y here. So then you should get negative 2x over 6y, or simply put, negative x over 3y. And as you can see here, for number 15, we get the same, so it's A. Nice work. And it also says satisfying over y, over 0, because I assume it's just a simplification, because that segment of the circle will look something like that, which is a bit easier, I think, to maximize at the very. Also, maybe to think about the gradient, it's a little easier in that way. Anyway, moving on. More Cobb-Douglas production functions. So for this one, I think it's pretty easy to notice, but just to avoid that with you guys. The isoquants for a Cobb-Douglas function are going to look something like this, okay? What they do is they essentially fan outwards in rays, sort of like this, and their asymptotes are going to be the axes, and they're going to just continue off infinitely in either direction. Obviously, like most asymptotes, they don't touch the axis, which is why C is clearly incorrect, because they can't meet the axes, right? So that's pretty much the closest, probably the easiest question on this. This is probably a difficult one. Now, I have a formula sheet for this. Let me bring this up. Okay. So, formula sheet. Where is it? So, for the... Okay, so we see here we've got a smooth function with a local maximum at AB. Okay, so it's any such point. Okay, so if it's has a maximum and at any specific point, then we need to find at that point what is the Hessian matrix. Okay, what the formulas say, if I can find them. Don't judge me here. Where is it? I think it's here. Yeah. So, at any local maximum, all right, you must essentially have, here we go. If the function has a local maximum at a specific point, then the gradient vector has equal to 0, and the Hessian matrix is a negative semi-definite. Okay, simple as it gets. Again, if it's a minimum, it's a positive semi-definite. Okay. It's a bit unintuitive, but sort of think about it like this. If it's a maximum, it's negative. If it's a minimum, it's positive. Okay, it's sort of like flipping around. Okay, so here the answer is going to be negative semi-definite, or C, as you can probably see here. Haha! Now, for concavity and convexity, you want to essentially state, is the Hessian matrix negative definite or negative or positive definite? All right, it should be that everywhere. All right, so here you can see that the answer is, wait, hold on, I think I may have denoted this wrong. Yeah, I probably did, didn't I? 18A? 18A. Yeah, it should be negative semi-definite. Sorry, there's an error in my thing. It's not very nice. Not very nice at all. So, the simple thing here is that if a smooth function is concave, okay, it must be negative semi-definite for all values. Okay, if it's convex, strictly convex, by the way, it must be positive semi-definite. But here it's negative semi-definite, so it is A. All right, I think I got this one wrong as well. Not particularly good. Anyway, let's think about this function here now. So, for the function here, which of the following statements is not true? Now, first of all, let's analyze these bit by bit. So, a homogeneous function. Okay, here it could be a homogeneous function. I could do lambda x to the power of 4, lambda y to the power of 4. Through some simple maths here, you can probably figure this out yourself. You're going to end up with a degree of 4, you know. So not exactly non-homogeneous. So thank God. F has a global minimum. Does it? Does it really? It does, actually. So to find that it has a global minimum, you can do the Hessian matrix here. The Hessian matrix for this one is going to, well, first of all, let's do the gradient vector. Deriving partially by x, you get 4x cubed, and then you get 4y cubed. And then for the Hessian matrix, I get 12x squared and 0, because deriving that by y would just give me 0 because it's a constant. And then we've got 12x squared. Now, that means that we can have a global minimum. We can have a critical point. Sorry, cough. We can have a critical point at 0, 0. And if we put this in here, well, what happens? You get a matrix that looks like this. Not great, is it? But what is actually this matrix? Well, the diagonal values are what? Okay, the diagonal values are non-negative, and the derivative is non-negative. So, it is sufficient for a positive semi-definite, essentially, okay? Which does imply a global minimum. Therefore, using that, actually, you can rule out C. The Hessian of F is positive definite for at 0, 0. It's not. It's positive semi-definite at 0, 0. There is a distinct difference between positive definite and positive semi-definite. If it was positive definite, you'd have something like this, okay? That would be positive definite. This is not positive definite. This is positive semi-definite. And you can see from also this that D is correct. D states the positive semi-definite, and F states that it's a convex function, which is also backed up by the positive semi-definite of the Hessian matrix. There we are. Okay, this next one is Lagrange. Hopefully you guys should be familiar with Lagrange by this point. Good old Lagrange. What did he do? Search on what Lagrange did. Lagrange. Probably a lot of Lagranges out there. Joseph Louis Lagrange. Ah, Italian. Oh my lord, the wig on this man. Oh wait, that's not a wig. I'm very sorry. Anyway, we're going to essentially minimize this with respect to the function there. X plus y equals 6. So L, which is the Lagrange, and then we've got x, y, lambda. This method should be baked in by this point. I don't expect most people to get this wrong, but I'm just going through it for completeness sake. So we have this function here, getting the partial derivatives of the Lagrange. We are essentially going to get y minus lambda, which is equal to 0, as we know from this sort of method. And then you've got to get x minus lambda equals 0. Thankfully then, x and y will both equal lambda. Okay? So now we can resubstitute lambda back into our constraint, and we get lambda plus lambda equals 6. So lambda must be equal to 3. There we go. And therefore, putting that in, we know that x equals 3, y equals 3. And therefore, our function, xy, is going to be equal to 9. So the max value we can get is e, or 9. Okay? And if we look at 20, 20e. Very nice. Okay. Now we're going to move on to the next one. Just wonder, how long have I been recording for? This is actually not too bad. Now consider the utility function. Okay, this is number 21 now. Consider the utility function. Stop telling me to sleep. Consider the utility function this, where x and y denote the consumption levels of two goods, and a and beta are positive constants, which the following functions will not give rise to the same demand function. Okay, here's kind of what you do. It's d, okay, but it's not exactly how you would expect it. Essentially what you do here is you sort of factor things out. So think of it like this. If I do u equals x alpha and x beta, we're going to go from here. Assume u is a constant, okay? U is any constant you want, anything, all right? Now, if u is a constant, let's go through all of these by themselves, okay? So, u is equal to x 3 alpha and y 3 beta. What we can essentially do here is we can factor out these 3's. Now, you can see that essentially they're times to it. So we can do x to the power of 3 x alpha, and then y to the power of 3 y alpha, or y beta. And you can essentially remove these, okay? So you get you can essentially just put them down here, right? Out of the way, out of mind, all right? Now, what this is essentially going to give you here is a new constant on your left-hand side, because you've essentially removed both of them, all right? Actually, wait, this doesn't exactly work. No, I don't think this method actually works. Now, how I actually did it was not exactly like this. It's because I may have derived them. So if you derive these, you may get a similar thing, if that sort of works. If that sort of makes sense. If that sort of works. Does that make sense at all? I wonder if it does. Okay. So, what I mean to say here, what do I mean to say? It's all very weird. Yeah. Well, the main thing to note here, actually, yeah, because, yeah, oh my god. No, I think the previous method did work, didn't it? Yeah, okay. But the main thing here is that, no, I was completely correct, wasn't I? Yeah. So, I'm sorry for that whole intermission. So we have u3 alpha, this is for A again, 3, and you're going to essentially take out the 3's and move them to the bottom here. Now, why does this matter? Well, essentially here, this is not the utility function. This is essentially just a value, okay? You have values of x and y, and you're essentially putting them under there, just for sort of safekeeping. This is essentially going to be the exact same function, okay? Because you've got x alpha and x beta on the same side, all right? So it's essentially the same thing. And then you've got b here. This is essentially the same thing as well. If you've got u is equal to 2 x alpha x beta, You can divide by 2 on both sides. The constant's just going to change, but it won't matter that much because it's going to be essentially the same thing. So you can express this as u again. So that kind of makes sense. C is another way of writing that utility function. It's just another method. It's literally like, so if you remember your log rules, you can take the number at the front of a log and then move it to there. So you can essentially have ln x alpha plus ln y beta. And if you remember log rules again, if you add 2 logs, you can times them. So you can have ln x alpha y beta, which is going to be equal to the u. And then you can essentially put everything to the power of e. So you could have something like x alpha y beta. Why did I say y beta? It sounds like wife beta. That's not very good. Anyway, but you have this new utility function here. And it's essentially going to be the same constant. Now, what is the odd one out here is d. Because you can see on d that 2 alpha and 3 beta don't cancel each other out in the same way, if you sort of think about it like that. So if I was to have 2 alpha y 3 beta equals u, then you essentially get u over x squared y cubed. These are not the same, which is the main thing. So they're not going to really cancel. And they're going to end up as, yeah, how do I put this? Yeah, just take my word for it here, is that this doesn't work. Essentially, if you can't remove anything, or you can't like make it into a new constant, you essentially don't have the same demand function here. Actually, wait. Hold on, let me pause and research this. I think I may have skipped over something. Okay, well, I'm an idiot. What this essentially is asking you is the MRS, and it's asking you for similar MRSs to both. So as you can see here, I've done the MRS for A. It ends up as minus alpha y over beta x. Now, if we do these for the others, you'll see a similar thing. Finding the MRS of this function is basically the partial derivative of u to x and over the partial derivative of u to y. So the partial derivative of u, of course, it's minus that. So essentially the formula up here will tell you that. So for this, you would get negative 2 alpha, x alpha minus 1, y beta, and that would be over 2 beta, x alpha, y beta minus 1. That would be that. And what you'd actually end up doing here is cancelling out the 2's, and then you'd end up with a similar thing up here, and then you get the same same MRS. So we're saying that it's the same function. Okay, doing the same thing here we've got with C. If you can sort of remember deriving ln of x, you get 1 over x. So you end up with alpha. Actually, again, it's a little easier to sort of think about it like ln. Well, actually, no. Well, it is kind of similar, I guess. But it is essentially the same thing that's happening twice. So if I sort of, well, if I actually like, screw this, I'm not doing this. Always use like a good differentiation calculator. You know? This will probably show it a little better than I can, to be perfectly honest. Let me just set implicit differentiation. So, ln of, no, not in of x to the alpha plus, I mean, it's technically the other way around, but sort of get the point. By the way, this site is very useful. I would recommend that you guys use it if you're ever struggling on just a quick differentiation. If you get stuck, there's always this one. So, if you do something like this, does this even do a partial derivative? Actually, it gives you it by implicit differentiation quite easily. So as you can sort of see here, you derive quite easily there. I don't know how I found that so well. That's so embarrassing. I do apologize. But essentially what you get at the end of this is you're going to get alpha x plus beta y which is going to be times by the dy dx, because you're doing it implicitly at this time, which is equal to 0. And rearranging this, you would get minus alpha over x is equal to dy dx beta over y, which eventually gives you minus alpha y beta x, which as we see up here is the same. Now, moving on to d, why that one's incorrect. So for d, you can see that if we essentially try to do the partial derivative here, doing the partial derivative of x gives you minus 2 alpha x 2 alpha minus 1, and then you've got that over 3 3 beta x 2 alpha y 3 beta minus 1. Now the thing is here, these numbers don't cancel. So it doesn't actually work here, okay? It just can't do the same thing. I won't go through B because you can, because you can clearly kind of see that it'll just factor out the differentiate out the constant there. Anyway, that was a long one. I hope my video can stitch together. I accidentally shut off my recording. The production function, FKL, denote capital and label respectively. Which of the following statements is not true? Now it's A. Now why is it A? Well, the production function is not concave. As a matter of fact, it is convex. Remember our definition from earlier. It is only concave if the matrix is negative semi-definite, okay? Which again means that the diagonal entries are non-negative. No, I think they're non-positive or something like that. Let me try remembering what they are. Yeah, negative semi-definite. Diagonal entries are non-positive and the determinant is non-negative. Okay? So, if we actually do this one, if we sort of start with dkdl, no, not dkdl, dfdk, dear me. So dfdk is going to end up just being L in this case. So we have L, and then it's similar for L, it's just going to be K. Then moving on from there, if you do any subsequent differentiation, you get, actually wait, oh. Yeah, because you'll get, no way, oh my god. Alright, so, oh no, it's because of the thing. Oh my god, okay, never mind, let's be doing this implicitly. No way, oh, to be technically completely honest, I mean, you could do this with the second derivative, okay? So if I was to, for example, do implicit differentiation on this, I would do the product rule, which would give me L plus K and then DL dk, I believe. Yep. And that would eventually give you minus L over K as the derivative. Then doing it for a second time, you would do 0 is equal to so because you're essentially deriving the minus k to the minus 1 here, it's going to become k squared. So you'll have L k squared, and then you're going to reserve that, you're going to differentiate that L and keep the k, so you'll have 1 minus k here. And this, in this case, you're differentiating the L, so we add the dl d squared L dk squared, and you get minus L k squared is equal to minus 1 over k d squared L dk squared, and then you can factor out those timeses. You can remove that one as this one cross multiplies, and yeah, you should end up with L over K. L over K. That's that. Now, by necessity, this one can't be positive either. It's just like, it's because the second derivative here essentially cannot exceed, what was it? Yeah, something about like second derivative here. One moment, let me just sneak a peek. Yeah, okay. So because we know that K and L have to be positive, this is the main thing. L over K has to exceed 0 in all cases. Because, well, first of all, K isn't equal to 0. It's always going to be above 0. and L is also going to be above 0, so it cannot be negative. This is the main thing here. So we're showing it's concave. No, we're showing it's convex, sorry. Oh wait, what the fuck? What did I do? Yeah, sure, sorry, that shows it's convex, because it's exceeding 0. Hold on, let me just... God, I'm really in a state today. Pause. I think I'm an idiot. Okay. When you get the Hessian matrix for this function, it is 0, 0, as is shown. Okay? It's... So if I was to partially derive it, I would get... Is that on there? No, it's on the screen. Oh god, this looks like such a mess. So if I partially derive relative to k, I get L, and if I partially derive relative to L, I get k. Therefore, the Hessian matrix is going to end up just going to 0 because you've got constants there. What a zero matrix is it is both positive definite, it's both positive semi-definite and negative semi-definite. Okay? This is because the determinant is both non-positive and non-negative because it's 0, and the diagonal entries are both non-negative and non-positive because they're both 0. Okay? So it's not concave. It's not convex either. It's neither of them. It's neither concave nor convex. Therefore, A is false. Because it's not strictly concave. It's basically... it's neither, is the main thing. God, I'm such an idiot. Oh, I feel so embarrassed. Okay, never mind. Let's continue. Okay, finally, some easy ones to end it. So a differential equation is pretty easy in this respect. This one is thankfully separable, but we don't actually need to separate it, we just need to move the dt over. So for this one, you have dy dt is equal to 2e 2t. What you do is you times by 2 dt on both sides, you get dy is equal to 2e 2t, you move the dt over here, and this is essentially timesing by 1. And now what we can do here is that we can integrate. So you have 1 integrated by dy, and you've got the integral of 2e to the 2t done by dt. This one's fairly simple, it's just going to end up as y. This one, as you can sort of notice, you're just dividing by the 2t there. So you just end up with e to the 2t. But then you're also going to have that extra c there, so you don't know what that is. That's what we've got to figure out. Now what it says here is that y is equal to 0 when t is equal to 0. So 0 is equal to e to the power of 0 plus c. Now e to the power of 0 is 1. So to equalize, c must be minus 1. Okay? Which gives us c as our answer. So c is correct. Now for 24. So for this differential equation, I first of all want to rearrange it into the form I usually like. This form is dy dt plus some value of y equals some value q. Okay? What I do that, well, if I want to do that here, I divide by 3 on both sides. So in this case, you have 3 dy dt plus 5y is equal to 120. What you actually get by dividing by 3, after all that, is dy dt plus 5 over 3y is equal to 120. No, pardon me, 40. It's equal to 40. Okay? Now the general solution for this, if I get up my formula booklet, if I can even remember any of my general formula. Yeah, so the general solution is this. Can I enlarge this? I cannot. Okay. The general formula is this. Y is equal to A E minus AT. The capital A would be the unknown here. It would be A. Where this number here is A, and this number here is B. Okay, so if I insert that into my formula, I essentially get y is equal to capital A, which we don't know, minus 5, so I have e to the power of minus 5 over 3t plus 40 over 5, 3. Okay, so 40 over 5, 3, so 40 divided by 5, 3 means I'm timesing it by 3/5 as well. which means it is 24. Okay. Now you can see here, that you've got sort of a constant of 24 here. Now, as t actually increases, as it says here, as t tends to infinity, that value of e is going to get smaller because it's going to increase its negative power, which is essentially going to drag it down to 0. So that left side of the equation is going to become entirely 0. So y would end up equaling 24. Therefore, b is correct. Now the difference equation, again, fairly simple formula to remember here. If I can just get it up. There we go. So for a difference equation, which we are given here as 3yt plus 1 plus 5yt equals 120. The formula for it, just looking at my formula sheet here, is yt is equal to b 1 plus c plus a minus c to t, where this value here will be c and this value here will be b. Now what we have to do first is make sure the yt plus 1 doesn't have a coefficient, so we're going to have to divide everything by 3. This means this 3 gets removed, this turns into 5 over 3, and this 1 turns into 40. Okay, now using this, we can go forward with this. So we now have 40 divided by 1 plus 5 over 3, which is going to be 8 over 3, which means we're going to be timesing it by 3/8, which in this case will be 15. Now we just add capital A minus c, which is going to be minus 5 over 3, then it goes to t. All right? Now, what happens in this case? Well, actually, the general solution will alternate around 12. Why? Well, as t increases over time, you're going to get varyingly smaller amounts of this variable over here. Eventually it will hit t, but it's going to essentially go around there until it gets there. This is essentially a difference equation. It sort of bounces around the solution until it gets to it. Okay, I think that's everything. Okay. Whew. Okay, I've hopefully explained every one of them. I don't know how effective that was, but I hope it helped. I'm aware that I stumbled on a few. I'm quite sorry. But hopefully this is good enough for you guys. All right. Okay. See you guys some other time. Bye.